All right, here we go for Chapter 20, Section 2, Stream and Lake Pollution. Surface water, streams, and lakes. Many streams and rivers around the world are actually polluted, not shocking given the title of the chapter. For the most part, streams and lakes can cleanse themselves of these biodegradable waste. Once again, something that is biodegradable if we don't overload them or reduce their flow. Once again, if there's flow coming in, well, any pollution that gets in it tends to wash downstream, get diluted out, and can take care of itself. But when we add excessive nutrients into the lakes from human activities, well, this disrupts the ecosystems and they can't handle the amounts. Things can handle levels of pollution. We've talked about wetlands, incredibly good at pulling out pollutants. Rivers and lakes will clean themselves given time, but when we keep adding more and more and more pollution, they can't keep up. By and large, preventing pollution is much more effective and a lot less costly than cleaning it up. We need to put as much of our efforts as possible into prevention so we're not in the business of having to spend millions and even billions of dollars when we talk about a country in cleanup efforts. If we could have stopped it from the beginning, we'd be so much better off. And all of our cleanup efforts are useless unless we stop the problem. Otherwise, we're just cleaning up forever. Now, the cleansing process is basically dilution and bacterial biodegradation. The bacteria break it down. A pollutant gets into the system, no matter what it is. It might be a long, complex chain of some sort of chemical, but in time, it breaks down. It degrades in the environment, and bacteria are a huge part of this, breaking waste down into simpler and usually less harmful components. This takes time. It can't work if the system's overloaded. Once again, too many pollutants kills too much. Remember, pollution, anything that degrades the system, that something needs to survive in it. So even the bacteria can be harmed and affected by the process. And it doesn't eliminate the very slowly degradable or non-biodegradables, plastics as one. Plastics are just not biodegradable. Nothing eats them, nothing breaks them down, and they just remain there. They just build up and build up and build up. As long as our pollutants are biodegradable, and a lot of times like sewage or animal waste, and the nitrates and the phosphates, these are biodegradable. They're part of the normal natural cycle of things, and in time, they take care of themselves as long as we work on the prevention to keep it from continuing to happen. Now, if you take a look at this stream here, we're going to look at what we call an oxygen Sag Curve. So we have a normal, healthy stream, and it might be a little hard to see, but we notice right in that one spot where the water starts to get cloudy, there's a pipe. We have point source pollution. So it's dumping into the water there. So we have a blue line and we have a red line. The blue line is to dissolve oxygen, and it's at 8 parts per million, 8 to 9 being good for a stream. Down at the bottom, the red line, this is going to be a biochemical dependent something. In other words, this thing needs oxygen. So we put the waste in, and the waste is going to use oxygen. So this biochemical dependence or whatever goes way up. It was down. There weren't that many biochemicals in there needing the oxygen. Now we get the point source, and that red line goes way up, and the oxygen line goes down. And this affects what can live there. Very few things can live right at that point source. Now, right where the point source comes in, we still have some fresh water coming in. It's right down from it, which is the worst area. So we get a few things that survive right where it's occurring because they're still getting some of the fresh water coming in. Right down from it, this is all mainly heavily polluted area, and very little of anything is living. Then as the water gets more diffused, dispersed, that oxygen sag begins to drift back up. And in time, the biochemicals that are demanding the oxygen get fewer and fewer, and that curve goes down. But this is a classic oxygen sag curve that we can note when we have a point source pollution. Now, what really gets bad is you get this sag, and a little farther on down the stream, you have another point source coming in, and the sag occurs again and again and again. And then you get a whole section of stream that's overloaded, and the whole thing becomes overly polluted, and it's no good to anybody. And unfortunately, we see this in a lot of places. We've seen it in the United States. We've done a lot since the 70s to try and clean up our waterways, but a lot of countries around the world are not, hence the problem. Now, stream pollution in less developed countries, not the United States, by and large, Asian countries, African countries, and South American. There are always exceptions, but in general, these are less developed countries. The cities are discharging 80 to 90% of their untreated sewage directly into the rivers, lakes, and streams. People are going to the bathroom, and it's going directly into the river. Untreated waste going straight in. They're unable to afford the water treatment plants. Here in the United States, we pay for our water. It's metered and we have to pay for it. What are we paying for? By and large, not the water. We're paying for the treatment of it. We're paying for the treatment so it's safe to drink, and we're paying to treat it before it's put back into the systems. But lots of countries simply can't afford the water treatment plants, and they don't treat it. It's dumped right back into the rivers and streams. They're just dumping it downstream from the city, but of course whoever lives downstream is full of waste, and then you get into another city and another city and another city. In a lot of these places, they just don't have, or they do not enforce their water pollution laws. A lot of the places, they put water pollution laws on the books, but nobody enforces it. So even if a factory is just dumping directly into the stream, nobody's doing anything about it. The picture you see here, this is in India, and the truck is just backing up and just dumping waste directly into the river. It's illegal, but there's nobody to enforce it, and nothing happens. Half of the world's 500 major river systems are polluted. So 500 major river systems, 250 of them are polluted, mainly untreated sewage and industrial waste. This is what's going into them. And unfortunately, this is where everybody needs to get their water. Surface water is where most poorer countries, undeveloped people get their water. They can't afford to pump it up out of the ground. Pay for the electricity, or even putting in a hand pump is still expensive. They're getting it from rivers and streams, and over half of them in the world are polluted. We're just talking the major systems. Lots of them are polluted that are not major river systems. This water is used for all kinds of human activities. People go there to bathe, either getting their water from it. Nearly half of China's rivers are too toxic to touch, let alone drink. If you were just to get in it and on you, you can wind up getting sick and hazards from it. Because some of that has toxic waste in it. There's liver and stomach cancer that's linked to water pollution, along some of these leading causes of death from water pollution. The picture back here is of the Ganges River. This is India's most holy river. People go into it to bathe all the time, and part of it is a religious ceremony of cleansing. But unfortunately, the river is just viral with waste. And it's unfortunately not uncommon in less developed countries for the rivers to really be in a horrible state of decay from pollution. Pollution of lakes and reservoirs. So streams, rivers, running, flowing water. Lakes and reservoirs are, by and large, lentic systems, right? They're not flowing. Low-tick flowing, lentic still water. Now there might be a stream coming in and a stream coming out, but by and large they're fairly still. So therefore they're less effective at diluting the pollutants. It takes a long time for all the water to cycle through, right? You have a stream coming in and a stream going out. But the flow coming in may be several hundred liters an hour, and the lake is massive, so it could take it a year or several years for all that water to eventually get cycled out. There's very little water through it. Can take up to 100 years to flush and change. Just depends on the size of the lake and the flow of the stream coming in and going out, obviously. We also get this biological magnification of pollutants, biomagnification, like we've looked at in a lab before. Pollution gets down in the bottom end of the food chain, and then something eats multiple of them, and the pollutants, there's more concentration in that organism than the next food chain up eats multiple of them, and we get higher and higher levels of pollution as it moves up the food chain. Biological magnification of the pollutants, or known as biomagnification. This is unfortunately very common in lake systems, which is why we're often told, don't eat the fish from this lake, don't eat the fish from this area, because we know biomagnification is occurring. Cultural eutrophication, as my mom is famous for saying, right? Too much of a good thing is can be a bad thing. And here it is, straight up. Eutrophication, the natural enrichment of a shallow lake. It happens just normally over time. The leaves blow in, animal waste makes its way in, and it gets eutrophication. This is normal. River mouth, a slow moving stream, it tends to happen a little faster. When it's caused by runoff and plant materials such as nitrates and phosphates, then a lot of times we talk about it being cultural eutrophication. Once again, when it's man-made, if you will, or what's the word I want? Man sped up. When it is largely affected by man and not just natural occurring. Now, oligotrophic lakes, as we've studied before, these have very low nutrients and very clear water. But with the adding of nitrates and phosphates, by and large, is what things that plants desperately need to grow. But when these come in from human sources, mainly from fertilizers and cleaning detergents are our biggest sources of it, then we get the cultural eutrophication. Farms contribute to it, feedlots, once again the CAFOs, streets, parking lots, lawns, mining sites, sewage plants, all of these can and do lead to cultural eutrophication. Now, it's especially bad during hot weather or during a drought. When it's warm, things tend to grow more often, right? You know, our spring and summer, we get greater growth. The oxygen gets depleted. The warmer the water, the less oxygen it can hold, and it exacerbates the problem. Now, we can prevent and reduce cultural eutrophication certain ways. Once again, removing the nitrates and the phosphates. Now, when we talk about removing phosphates, that's you and I not using phosphates in a lot of our cleaning solution. I talked about in India, a lot of times they are washing clothes right in the river. So their laundry detergents going directly into the river, adding to this eutrophication. Happens in China, lots of less developed countries. Once again, I tend to talk about India and Nepal since I live there. I'm not picking on it, I've just seen it with my own eyes. We need to remove the nitrates, and also we need to recycle the nutrients into the soil. Instead of dumping stuff into the river, if we can put it into the soil, well, then it's just back to the normal, natural cycle of things. If we can get it in the soil where the plants need it there, it keeps it from building up in the water supplies. And we need to have methods to clean up lakes. We have to remove some of these excess weeds. We need to use, we can use herbicides and algicides, pumping in oxygen to raise the oxygen level up. And most lakes themselves will recover if the excess of nutrients is stopped. Of course, the problem with all of these is they are expensive. If we're going to remove weeds, well, people got to go out there and do it. We need to pay them. If we're going to use herbicides and algicides, well, once again, it's chemicals that we got to buy and put in the lake. And pumping in water, well, once again, we have to have something to do that. It takes equipment, electricity to do it, and a lot of places don't have the money, and all of it means nothing if we don't stop the problem. Prevention is the key. We've got to stop what's causing it before we can really even do the cleanup. Otherwise, we're just cleaning up forever. Now, let's look at a case study, pollution in the Great Lakes. The Great Lakes up in the northern section of the United States, South Canada, was split the line there. these are something like, I forget the exact numbers, but something like 20% of all the fresh water on the planet that's not an ice cap is in the Great Lakes. They are massive stores of fresh water. And a lot of our Northeast and Canada rely on them for their water sources. Back in the 60s, there were many areas with horrible cultural eutrophication. There were fish kills and contamination just like crazy. 1972, once again, 1970 was the decade of the environment, if you will. A lot of laws got passed, and we kind of looked around and realized we've got to do something different. Well, the Great Lakes Water Quality Agreement was struck between the United States and Canada. There were a lot of new or upgraded sewage treatment plants. We stopped dumping waste directly into the lakes, which is what we were doing. They were huge. We thought they could handle it, but they were getting overly polluted. This decreased the algal blooms, it increased the dissolved oxygen levels, and the fish catches dramatically increased from this. They also made bans of phosphate-containing household cleaners, lots of the areas right where they would go in, because once again, the water would get treated, but a lot of the phosphates would remain in the water, and it would make it back into the Great Lakes. However, unfortunately, many of the problems remain. The picture back here was from 2011. This is in Lake Erie, and it tends to be the greatest affected because it's the shallowest of all of the Great Lakes, but over 1/3 of the lake had an algal bloom of this nature. So you can see the boat kind of cutting across this huge algal bloom across the whole thing. There's been an increase in the non-point runoff. Lots more farms, agriculture, and we really can't blame this farm or that farm or that farm. It's a little bit from all of them because we've upped our fertilizing a lot to get higher yield from the crops. Atmospheric deposition of pesticides. Once again, we spray them and it gets up in the atmosphere. The Great Lakes are so large, a lot of it just makes its way back down into them just from the air. And even mercury, because mercury gets airborne and it cycles and it rains, makes it back in the lake. We also get things coming as far away as Mexico and Russia. A lot of these particles are very fine. They get up in the air from here to there. Wherever's downwind is the problem. You could be creating all kinds of toxic waste, but your town might be fine because it's all blowing down, landing somewhere else. So the Great Lakes is getting stuff as far away from Russia and Mexico inside of it. 25% of the fish that were tested even recently have unsafe mercury content. So we have done a lot there, but we're not done yet. The Great Lakes Restorative Initiative. Between 2010 and 2015, 1.3 billion with a B, was spent in the cleanup. It was focused on reducing the toxic pollution. Once again, prevention, we've got to reduce it. The cultural eutrophication, loss of wildlife habitat, invasive species. We've looked at the various zebra mussels, things that have come in, and soil erosion into the lakes. And it promoted a lot of wetland restorations. Wetlands are incredible at pulling pollutants out if they're allowed to exist and we don't overload them. It's a prevention approach. We've got to call on bans of a lot of the toxic chlorine compounds that are used in pulp factories. We're trying to prevent these things, but unfortunately, a lot of the companies have lobbied successfully for these things not to be banned. They say, oh, it cost us too much money. Yeah, well, $1.3 billion spent in 5 years doing cleanup. But if we don't prevent the toxins from getting in the lake, we're going to be forever spending billions of dollars. It's not too high a cost to ban some of these pollutants from the people using them in this area. They're going to have to do it somewhere other than where it affects such a huge water supply. Guys, that wraps it up today for our lakes. Next time, come back and we'll look at groundwater.